Hello, everyone. I am Álvaro Garcia, and I want to thank you all for attending this webinar, where Hugo, who will do most of the talking, and I are going to share our experience using Gurobi to solve real-world problems and, in particular, complex vehicle routing problems. This is today's agenda. I will first say a few words about who we are and what we do. And following, I will introduce VRPs and some of its variants, and I will characterize briefly our problem within that framework. And after that, we will take over and we'll describe in detail the problem and the solving strategies we devise to solve it in a reasonable computational time. And he will discuss which worked better and why. And finally, before the question and answer time, we will share some lessons learned from our experience in general and from our work in routing with this problem specifically. So, BOAB is a spin-off of the Technical University of Madrid, Universidad Politécnica de Madrid, which was founded 9 years ago. And we were born with the mission of assisting our clients to make better decisions using advanced analytics. And by better decisions, what we mean is hard dollar earnings. What we do has a direct impact, which is measurable on when it comes to the bottom line. Our customers, as you can see in the slide, are mainly large companies, Fortune 500, because it's natural that the larger the companies are, the more complex their problems are as well, and the more the advantages that can be gained from using advanced analytics. And the core of what we do is depicted in the pyramid, which is on your right. It's structured in 3 layers. At the very bottom, what we have is descriptive analytics, which consists in making sense of large amounts of information, processing, synthesizing, displaying information. And this is valuable because it allows us understanding where companies are. And in the routing context, that would be something like having information such as a vehicle's utilization rate or costs per kilometer or costs per parcel delivered in the past. On top of that, we have the predictive analytics layer, which is more valuable and consists in foreseeing how things can be in the future or extrapolating past information. For example, in our case, we can forecast tomorrow's demand so that we can be better prepared for creating our routes for tomorrow. And this provides more value, as I said, but still the decision is something that depends on the decision maker, which has to do his or her best with the information he or she has. And the decision relies on the experience of the decision maker. And at the very top, we have prescriptive analytics or operations research, which is the more valuable layer because it is where money is. And this consists in suggesting, prescribing the optimal solution to whatever problem we are dealing with. In routing, as we will see later on, that will mean getting the routes with a minimum cost, for example. And this can and should be built on top of the previous layers because there is relevant information that can be obtained from those layers, such as the cost per kilometer or tomorrow's demand, which are absolutely relevant for making the decision and making or getting the decision that makes sense is actually feasible. We do all that can be included in those 3 layers, but where we are most useful is when it comes to OR with the prescriptive analytics. And we invite you to visit our website if you want to learn more about us. And now let's get with the VRPs. So before presenting our problem in detail, I will spend a couple of minutes, just that, on VRPs in general and some of its variants, although many of you probably are very familiar with them. A vehicle routing problem in its simpler version consists in visiting a set of customers like those you can see in that graph, which are represented by dots, orange dots. And these customers have to be visited using a fleet of vehicles departing and returning back to a depot. We have several routes, one for each vehicle, and as I said, you have to visit all customers in the map. And the objective is to optimize some KPI, typically related to cost, reducing the number of routes or the total distance, or taking into account some penalty for delivering with some delay. And you can have a combination of these KPIs to have an estimate of the relevant KPI, which typically, as I said, is related to cost. Small problems can be solved efficiently by experienced humans, but as the problem size increases, that is not an option unless you want to lose lots of money and time. And this can be even more complex when you take a look at some of the variants we might have, like those you can see in this slide. This is not a comprehensive list, just a few examples, and you can have, for example, vehicles that are all of the same kind. You have homogeneous fleets or not, heterogeneous fleet. You can have several depots or just only one. You can take into account and reflect in your model the fact that vehicles have a limited capacity, or on the contrary, this a requirement can be not taken into account because you can assume their capacity is unlimited. Vehicles can both deliver big goods, which makes sense with vehicles are capacitated. You can have even some discipline for pickup and delivery, like a last in, first out discipline. And customers can have time windows within which they can be visited, or finally, you can have distances which can be symmetric or not. This is just an outline or a set of examples, and you can have variants combined into more complex problems because you can find several of those features in a single problem. You can have capacitated problems combined with time windows, or capacitated problems combined with pickup and delivery. And reality naturally is very complex, and you can find a wide range of possible situations. Pretty much you can have as many problems as customers you can encounter. And in our case, within that framework, our problem, which will be described in detail by Hugo later on in a minute, we can say that we have two synced VRP problems where we have actual trucks, which are not only vehicles in mathematical terms, but actual trucks with their corresponding drivers that carry goods. And in addition to that, we have operated teams different from those of the trucks. So we have different resources that have to move to our customers to perform different tasks, but they have to do that in a synced manner. Our fleet is both capacitated, we have limited capacity in our trucks, and homogeneous. We consider a single type of vehicle, and we were considering only a single depot. And finally, there are two relevant KPIs which are in conflict with each other, as is always the case. One is the cost, naturally, and the other is the customer service. By means of using mathematical models, we can provide the decision maker with different solutions, although it's up to him or her to decide how to solve the trade-off. But we can provide him or her, for example, with given a certain level of service, the minimum cost to obtain that. Okay, that is how our problem is, if we have to characterize it in terms of VRP, the VRP framework. And now Hugo is going to describe this in more detail and present how we have solved it in a real situation. So Hugo, please, the floor is yours.
Thank you, Alvaro. So in the next slides, we are going to describe the problems that we had to solve at Baobab Soluciones. First, we are going to describe the context, then the inputs and outputs, and finally explain why it's a difficult problem. So in our problem, we have a number of sites that we have to visit to pick up products. To do that, we have a fleet of vehicles available and also a number of operators teams. The vehicles have to visit the sites in order to pick up the products. And the operator teams have to get to the same sites to prepare the product beforehand and then help to load them into the vehicles. The number of products to pick up may be different at each site, and this has an impact on the time necessary to load the products in the vehicles. The capacity of each vehicle is also determined by the number of products it can pick up. There is a time windows for each site, which may be different from site to site. And also, since the service is performed early in the morning, the clients prefer to be visited as late as possible, but still within their time window. So the hour of visit weighted by the number of products picked up is what defines the quality of the service. Our operator teams can work from site to site if they are close enough, or they may use some vans that will pick them up and move them to the next site. And finally, there is also a time windows constraint at the depot, and the vehicle must be back before a given hour. So there are two types of costs associated with the service. There is a cost related to the distances covered by the vehicles, and there is a cost related to the duration of the routes and the hourly costs of the drivers and the other team's operators. And this problem also have two different goals. One goal is to minimize the costs, and the other goal is to maximize the client satisfaction, which is measured by picking up as many products as possible, as late as possible. So as we described, we have a depot and several sites to visit. We also have a fleet of vehicles, and we need to create routes for them in order to visit all the sites. We also have a number of teams, and those teams have to get to the sites in order to help the vehicles. And as we said, the teams can either walk between sites or they can be picked up by a van. So as a summary, we have to coordinate and synchronize the routes of all the vehicles with the pass of the teams in order to have them together at each site. Now we are going to look at the inputs and outputs of this problem. So as input, we have the number of items to be picked up at each site and the associated loading times. We also have the vehicle capacities and the number of vehicles. We have the sites and depot time windows. And we have the distances and travel times between sites. And our aim is to obtain the following outputs: a vehicle schedule, a team schedule, and a van schedule. And we need to obtain those outputs with those two objectives in mind. So we need to maximize the quality of service, which means visiting sites as late as possible. And we also need to minimize the total cost of the service. About the vans, we realized early in the process that the vans were not critical aspects of the problem, because they do not cost as much as the other vehicles, and they are not needed so often. So we figured out that they could be considered as a small independent problem that will be solved once the solution for the vehicles and teams is validated. So we still did mention the vans in this webinar because they are a good example of elements that make real life problem more complicated, but which can be simplified by solving them in an independent problem. So from now, we are not going to talk further about the van problem in the rest of the presentation. Now that we have the problem clearly defined, we are going to talk about its difficulty. So I'm not going to talk here about hard as in NP hard, since any vehicle routing problem is already NP hard. But I'm going to talk about hard as why it is difficult to solve. So why is problem hard to solve? First, we have to take into account vehicle capacity and time windows. And because of this, any combination of sites in a route may not be valid. It may contain too many products to pick up for a single vehicle, or have some sites being visited outside of their time windows. And these characteristics make it harder for a solver to find a good solution. Then we have two objectives, cost and quality of service. Those two are conflicting goals, and finding the right balance between them make it hard for the solver to improve the solution and reach the optimal. We also have the double VRP characteristic of the problem with vehicles and teams that need to be synchronized, and that adds an additional layer of complexity. And finally, we also realize that there is no obvious good strategy or heuristic to solve this problem, because we could think of a strategy that would be to create the routes by always going to the next closest site. That way, we will get short routes, and so the vehicle would travel little kilometers and would have low costs. But if we do that, we may not have the best quality of service. Then we could think about spreading out the biggest clients in different routes. That way we could visit the biggest clients at the end of each route and visit them as late as possible. But it may not be a cost-effective solution. And then we could also try another strategy that would be getting all the biggest clients in a short route and make longer routes to visit the small clients. That would allow to have a short route that which is made late in order to have a good quality of service. But depending on the clients, that may not be an effective solution either. So by trying to solve smaller instances, we realized that sometimes the best solution was obtained with one of those strategies, sometimes with a mix of them, and sometimes the best solution was something totally different that we couldn't obtain with those strategy. So there is no obvious way to always get a good solution, and that's also why this problem is hard to solve. So we have defined the problem, and we are now going to talk about how to solve it. So first, we are going to discuss formulations, and then we are going to talk about the approaches we used to solve the problem by decomposing it in smaller problems. So we decided to solve this problem as a mixed integer linear problem with Gurobi. So there are several options to formulate a planning problem as a mixed integer linear problem. So the most straightforward approach is to discretize time. In the formulation, we use variables, but the logic behind that is just like making a planning in Excel. We separate the time into cells of 5 minutes, for example, and then we assign those cells to the task we need to perform. So to visit the different sites. This approach is quite simple, but as the problem grows larger, it will need a very large number of cells or variables to represent all of the times units for each vehicle and each site. Then a second possible approach is using time slots for a vehicle. In that approach, we consider that each vehicle can make a maximum number of visits, for example, here 3. And we assign this number of time slots to each vehicle. And then we create the planning by assigning the tasks to the time slots. And we also use other variables to decide when a time slot starts and ends. So the drawback of this method is that we will need enough time slots for the longer routes. And so many time slots will be unused in the other routes. Thus, we will need a lot of variables and constraints in the definition of the problem. And finally, we can define the planning as precedences relationships between tasks. So we can use direct precedences, which will be A is before B and B is before C, or general precedences, which is A is before B and C, and B is before C. And we finally chose the last approach for several reasons that we are going to discuss further in the next slide. So the general precedence formulation will use two kinds of binary variables to make decisions. The first variable, the route variable, will decide if a site is visited by a vehicle. In this example, the variable will be 1 for vehicle 1 and sites A, B, and C, and it will be 0 for all those sites and vehicle 2. Then we have the precedence variable, which will tell if a site is visited before another or not. Since these precedences are general, the variable will be 1 for A and B, but it will also be 1 for A and C because A is also before C. And it will be 1 for B and C. But it will be 0 for all the opposite relationships or when two sites are not in the same route. Then next, just like in the time slots formulation, we have continuous variables deciding at which time a site is visited, so start and end. And finally, we have here the constraints that will be used to link start and end times with precedences. So this constraint means that the end time of site A plus the travel time between site A and site B is smaller than the start time of site B plus a big constant M times 1 minus the precedence variable between A and B. And this constant is named the big M, and it has a value which must be higher than any of the other variables. And so that means that if A is before B, then this precedence variable will be 1. So we will have M times 1 minus 1, and this part will be cancelled. And we will just have a relationship that will force the end of A to be before the start of B. And on the contrary, if A is not before B, then this precedence variable is 0 and the big M is activated. And then the constraint means that the end of site A is smaller than a variable M, which is always bigger by definition. So the constraint will do nothing in that case. So obviously, the complete formulation of this problem involve many other variables and constraints, but we will not go into these details in this webinar. So this formulation has several advantages. One is that the number of binary variables is relatively small, which makes the problem easier to handle by the solver. And also another advantage is that a site can be moved from one route to another by only changing few variables. For example, we could remove site B from the first route by only changing the precedences where B is involved. And if we do that, the relationship between A and C won't change. However, the use of big M in that formulation is a trick that makes the problem significantly harder to solve. Still, the trade-off between the number of variables and the massive use of big M is in favor of this formulation. We first try, for example, the time slot formulation, and it did perform significantly worse than the general precedence formulation. So our first attempt was to solve the problem with the precedence formulation. So we did generate some random instances of the problem of different sizes and tried to solve them. Gurobi did solve the small instances very quickly, in less than 1 second. But it took several minutes to find feasible and good solutions for the larger instances. So we tried to help the solver find feasible solutions faster by decomposing it in smaller problems. It did work and got us feasible solutions faster. However, those solutions were quick to find, but not always very good. Finally, we managed to find ways to improve those solutions with a local search based on the decomposition and still using the MILP formulation. So the first decomposition was quite simple. We solved first the vehicle problem, we fixed the routes, and then in a second time, we solved the team's problem. So this decomposition focus on finding a good or optimal solution for the vehicle planning, and then try to make the team planning works. Then we tried another idea for decomposing the problem. So in this idea, we grouped different sites together. We solved the problem for the first group of sites only. Then we fix the route assignation and the precedences in the solution. We add another group and we solve again. And we continue until all the sites are in the solution. So by building up a solution that way, we can get to a feasible solution for a large problem really quickly by only solving very small problems. But the main drawback is that the solution may not be very good, since the last groups of sites do not have a lot of options left when we solve their own small problem. Because of that, we thought about ways to improve the solution further. So we saw that we could build up a complete solution by solving smaller problems, and we obtained a feasible solution, but not always a very good one. So we realized that we could actually improve this solution by solving the small problems again. So following the same logic as the last decomposition, we used the following steps. We choose some sites randomly in a feasible solution. We remove those sites from the solution. We fix the routes and precedences in the solution, and we solve the problem again for those freed sites. And we can repeat those steps several times in order to create a small local search algorithm based on the iterative decomposition and the resolution of small mixed integral linear problems. This local search worked pretty well, but we noticed that many times the sites freed randomly couldn't really be reassigned in a better place, which meant that the solution was slow to improve. So we figured out that a way to allow some easier reallocations of vehicles and sites in the solution was to free entire routes at the same time. So to do that, in order to do that, we select randomly 2 distinct vehicles, and then we free all the sites for those vehicles, and we fix the rest of the solution. And we solve the model again. This way, we can mix the sites from 2 routes in order to get a better solution. This vehicle local search algorithm did allow quick improvements of the solution. Its main drawback, however, it's that especially for small scale instances, the algorithm may optimize all the possible pair of routes and get stuck at a local optimum. So we also tried mixing both local search algorithm in order to get the best of both worlds. So this way we would get the better performance of this vehicle local search and the higher randomness of the site local search, which can unlock some good solutions that wouldn't be accessible otherwise with the vehicle local search. So as I said before, we did generate several instances of the problem of different size, and we tried many different combinations of the different methods that we have presented. So we are now going to look at the results and draw some conclusions from them. So we generated instances of the problem of different sizes. We had small instances of 8 sites, 2 vehicles, and 4 teams. Then medium instances of 20 sites, 5 vehicles, and 10 teams. And large instances of 40 sites, 11 vehicles, and 22 teams. We solved the problem for several instances of each size, but we will only present one example of each size here. So we did try to solve each instance of the problem with different combinations of the methods that we presented. So we tried it with the complete precedence model, with the first two-phase decomposition, with the second iterative decomposition, then with a combination of both decompositions. And we also try combining the decompositions with the two mill-based local search algorithm. So the vehicle local search and the site local search. So we solve each instance several times with different solving times. We tried in 1 minute, 5 minutes, 10 minutes, and 30 minutes. And we looked at the best solution we could obtain in this time limit. So the results shown as a percentage in this table are the differences between the methods, between the solution obtained by this method and the best solution we found for this instance with any method. And this best solution may be the optimal solution. It is for the small instance, but it also, for the larger instances, it's only the best solution that we found with any method without any guarantee of it being optimal. So the timeout text, which appear in the table, appears when no solution was found in the given time. It happens for medium and large instances when we try to solve them in 1 minute. Then we also have some infeasible text, and this text appears when the resolution was stuck with an infeasible problem. This happens with the iterative decomposition when the last group of sites cannot be allocated. We can also notice here that the precedence model alone works pretty well for small and even for medium instances, which are solved in less than 5 minutes, but that the problem gets a lot harder to solve with the larger instances. In some case, we can also see that in some case we can get better results in 10 minutes than in 30. This is due to the randomness in the local search algorithm. So we may have been lucky and found a very good solution in the 10 minutes resolution, but we didn't explore this same solution in the 30 minutes resolution, so we didn't find a solution as good as the other. We can also notice that the columns using vehicle local search here are pretty green, and that means that they have most of their solution which are only 5% worse than the best ones. And that shows that this algorithm is quite effective. A last interesting note here is that the solution found in the last column for 40 sites here is better in 1 minute than the solution found by the full model, by the complete model in 30 minutes. So that also shows that the method using the decompositions and local search allows us to find very good solution very fast, very quickly. And now Alvaro will present the general conclusion of this study.
Thank you very much, Hugo, for your presentation and your discussion. And just as a wrap up to everything we've been seeing in today's webinar, I wasn't just to highlight that if VRPs, just plain VRPs, are hard to solve, let alone real life VRPs, as the one we have discussed in this webinar. And companies should invest in having efficient techniques to obtain routes in an efficient and effective manner. And what we can say is that mixed integer linear programming models solved at once with Gurobi are an effective and efficient way when you have small and medium-sized problems and you prove optimality. And when you have larger problems, you have to resort to other strategies, and you can decompose the problem, and depending on the nature of the problem, you can combine different types of decompositions with local searches using as well mathematical models, which is something that allows you to explore very fast and not losing feasibility, because if you tune the solution, you can easily lose your feasibility, as is the case here, and you can keep that during the mill-based local search. And this all, using this kind of approaches with Gurobi, means saving time and money. And it's also, it's not only a thing related to getting very good routes, which is the case, but reducing the planning time and allowing the managers to use their time for something more valuable than composing the routes or solving something which is very complex using typically Excel. They can replan and explore different scenarios, playing around with different weights for service level and for cost, and eventually implementing whatever is best for their case. So it's a way to use the best way the time of the managers and allowing them to have better tools to do their work. So this is all we wanted to share with you.